All right, guys. So we're going to start off with chapter 1, okay, which is reaction kinetics. But before we get into the chapter, we're going to go over the significant digits, okay, sig figs. You must have done this in younger grades as well. So we'll do a quick recap, okay. If I give you 324, how many sig figs are there? Oh, 1, 2, 3. All of these digits, they all matter. So we have 3 sig figs. Okay, what if I make it 3240? In this case, the 0 at the end is not going to count. So it's only 3, 2, and 4. So we still have only 3 sig figs. What if I give you 3204? Well, we know 3 is a sig fig, 4 is a sig fig. So every digit in between is a sig fig as well. So how many sig figs do we have? 1, 2, 3, 4. So we have 4 sig figs in this case. What if I give you 3.20? Now, guys, usually if you have a 0 at the end, it does not count. But if you have a 0 after a decimal, as long as there's a non-zero number in front of it, it's going to count. So in this case, you have 1, 2, 3 sig figs. But what if I give you 0.05? Well, in this case, you know, normally the 0 after the decimal would count. However, the number in front of that is just a 0. So these zeros are not going to count in this case. You only have 5, which is your significant digit. So you only have 1 sig fig for that. So remember this, 0 after the decimal counts only as long as you have a non-zero number in front of it. Okay, so using the same concept, what if I give you 3.020? Well, you know, 3 counts. The 0 at the end is going to count because it has a non-zero number in front of it. And again, it doesn't need to be right here. As long as it's in front of it at some point, it's going to matter. So in this case, 3 is a sig fig. This 0 at the end is a sig fig. So everything in between is a sig fig. So you have 1, 2, 3, 4. 4 sig figs. Are you understanding it so far?
Yeah.
Sometimes they're going to write it as a scientific notation. So they might give you 3.20 times 10 to the power minus 2. Well, you don't really care about this 10 to the power minus 2 or any other number. You just look at the main term. This is your main term, 3.20. 0 after the decimal is going to count now. So this counts, 0 counts, everything in between counts. So you have 1, 2, 3 sig figs. Fairly straightforward so far. So let me give you a couple more examples. What if I give you 9.080 times 10 to the power minus 3? 9 counts, this 0 at the end counts, so everything in between counts, so you have 4 sig figs. Okay, what if I give you just 9? Well, in this case, you only see one number, so you just have 1 sig fig. What if I give you 320,000? How many sig figs do we have here? So in this case, there's no decimal, so these zeros at the end, they don't really matter. So it's just 3 and 2. You only have 2 sig figs in this case. Okay, so 1.00. Now the zeros after the decimal are going to count because they have 1, which is a non-zero number in front. So you have 1, 2, 3 sig figs for that. Fairly straightforward, okay? So this is the basic of sig figs. Now, you need to know your sig fig rules for multiplication, division, and for addition, subtraction. Okay, those rules are a bit different. So first we're going to talk about sig figs when it comes to multiplying and dividing. When it comes to multiplying and dividing, what's the rule? Well, we're going to do an example because an example is going to explain it in the best fashion. What if I give you 32.52 and I ask you to multiply this with 2.1? All you would do is you would just blindly punch it in your calculator. So take 32.52 and multiply that by 2.1. If you do that, this will give you it will give you 68.292. It will give you 68.292. But now we need to worry about our sig figs. How many sig figs did we have in the first term? 1, 2, 3, 4. I have 4 sig figs in the first term. How many sig figs do we have in the second term? We only have 2. Okay, so remember this rule. Whenever you have two numbers which are being multiplied or divided, your answer should have the least sig fig out of all the numbers. Your answer should have the least sig fig. So your answer should only have 2 sig figs there. Right now, how many sig figs are you seeing? You're seeing 1, 2, 3, 4, 5. Okay, that's not going to fly. We need only 2 sig figs. So 68.292, to make it only 2 sig figs, you will just round it down and write it as 68. A lot of people, sometimes they have problems writing sig figs whenever you have too many numbers. So another thing I would recommend is, you know what, you can write this as the scientific notation. How would you do that? You would put the dot after the first number, after the first digit. So this becomes 6.8292 times 10 to the power. Now it's right here. The decimal is right here. You moved it one place to the left. So it will be 10 to the power 1 because you moved it one place to the left. And now you look at this, you say, okay, I have 5 sig figs right here. So that's not fine. You want to write it as only 2 sig figs. So you're going to say, you know what? I will just write this as 6.8 times 10 to the power 1, which is same as 68. So there's 2 ways to write it. You could have just written 68, or you can write it as 6.8 times 10 to the power 5. Does that make sense?
Yeah.
Okay. So when it comes to multiplying and dividing, you're going to pick the least sig fig. So let me just write it over here. Least sig figs. Your answer should have the least sig figs of all numbers involved. Of all numbers. Okay. Let's have a look at another example. What if I give you 32.56 divided by 2.3? Okay, this is divided by 2.3. You would just blindly punch it in. So just take 32.56 and divide it by 2.3. It gives you 14.1565. Okay, so then you ask yourself, how many sig figs did I have here? Well, this number has 4 sig figs. What about this? This has 2. So your answer should have the least sig figs out of all the numbers involved. Means your answer should have only 2 sig figs. So you will just write this as 14. And now you only have 2 sig figs. So far, so good. Do you guys have any questions?
No.
Okay, excellent. Let's have a look at another example. Okay. What if I give you 9.0 times 10 to the power 32, and I ask you to multiply this with 3.0000. Again, as usual, you would just blindly punch it in. When you blindly punch it in, you will get 2.700, blah, blah, blah. You can carry on, raised to the power 10 to the power 33. But then we need to look at the sig figs. How many sig figs did 9.0 have? 2. The 0 after the decimal is going to count. What about this? Now, all these zeros after the decimal are going to count. 1, 2, 3, 4, 5. My answer should only have 2. Right now, I'm seeing 4. So I need to fix that. This will just be 2.7 times 10 to the power 33. Any questions?
No.
Okay, good. Let's have a look at another example. What if I give you 2.020 times 10 to the power 3? And we multiply this with 2.8, 1, 2, 3, 4 times 10 to the power minus 2. Okay, so we blindly punch it in. So make sure you put brackets, 2.020 times 10 to the power 3, bracket close, multiplied by, put another bracket, 2.8 times 10 to the power minus 2, bracket close. When you do that, you get 56.56. But then you got to say, okay, how many sig figs did I have here? Well, this one had 4, right? Mm-hmm. And what about this? This one has 1, 2, 3, 4, 5, 6. So the answer should have 4 sig figs. Well, this one already has 4, so we're fine for this. What you could have also done was when you got 56.56, you could have written this in scientific notation. So this would have become 5.656 times 10 to the power. You move one place to the left, so 1. And again, you have 4 sig figs, so either or works. Both of these answers, they have 4 sig figs, and you've just written it, one in scientific notation and one without. Okay. So fairly simple when it comes to multiplying and dividing. Okay, let me give you another example. What if I give you multiple terms? What if I give you 98.273 multiplied by 9.8 and we divide it by 8? What will my answer be? So let's punch it in. 98.273 multiplied by 9.8 and we divide it by 8. It will give me 120.38. So, okay, now let's look at the sig figs. This one had 1, 2, 3, 4, 5 sig figs. This one had 2 sig figs. This number only had 1. So my answer should only have 1 sig fig, right? Oftentimes, people have problems writing this as a 1 sig fig. You can't just make it 1 because 120.3.84 is not 1. The best way to do that is, you know what, first let's write this as a scientific notation. So it will be 1.20384 times 10 to the power. Okay. The decimal is here. We're going to move it to the left. 1, 2. I had to move it 2 places to get to after the first number. So it will be 10 to the power 2. Okay. My answer should only have 1 sig figs. So we're going to write 1.20384 as only 1 times 10 to the power 2. Or if you really didn't want to use scientific notation, this 120.384, if you want to write it only as 1 sig fig, you could have just written this as 100. And that has only 1 sig fig. 100 and 1 times 10 to the power 2 are exactly the same. Fairly simple, correct? So this is your rule for multiplication and division. So let's talk about addition and subtraction now. How do we tackle our addition and subtraction questions? Plus and minus. Well, the rules for addition and subtraction is a bit different. If I give you 28.94 and I say minus 1.2, as a first step, you would just blindly punch it in. So you say 28.94 minus 1.2. It gives you 27.74. But when it comes to plus and minus, you look at numbers or you look at digits after the decimal. You look at digits after the decimal, and obviously you use the least out of all. It will make more sense when we look at this example. So ask yourself, how many numbers did we have after the decimal? Now guys, we're not looking at the sig figs. We're just looking at the numbers after the decimal. This one had 2. How many numbers did this have after the decimal? 1. My answer should have the least out of those 2. Means my answer should only have 1 number after the decimal. So your answer will be 27.7. Okay, do you understand? So when it comes to plus and minus, you only look at the numbers after the decimal. What if I give you 2.345 plus 2.1? So let's blindly punch it in. 2.345 plus 2.1 gives you 4.445. 4.445. Then we say, okay, let's look at the numbers after the decimal. We have 3, and over here, we have 1. My answer should have the least out of those. My answer should only have 1. So you would say this is 4.4. Okay, let's have a look at a couple more examples. What if I give you 320 plus 1,000? So when you add them up, you get 1320. Okay, but now we got to look at the numbers after the decimal. How many numbers were there after the decimal? 0. How many numbers were there after the decimal? 0. My answer should have 0 numbers after the decimal, which is already the case. So that's my final answer. So far, so good.
Mm-hmm. Yeah.
Okay. What if I give you 0.0054 plus 0.12? So let's add this up. 0.0054 plus 0.12. It gives me 0.1254. 0.1254. We got to look at the numbers after the decimal. This one had 4 numbers after the decimal. This one had 2. So my answer should only have
2.
at least out of those 2. Okay? So my answer should only have 2 numbers after the decimal. What do you think that will be?
0.13.
Exactly. You'll just round it up and you'll say it's 0.13. Okay? So far so good?
Yeah.
Perfect. So that's how you're going to tackle your plus and minus questions. Now, sometimes they might give you a combination of multiplication and division. So how do we tackle that? Let me give you an example. What if they say we have 98.35 and we multiply this by 1.2? Then we say plus 8 times 25.2. So what we're going to do is we're going to first do the brackets. Okay? So we do 98.35 times 1.2. That gives you 118.08. But we have to use our multiplication sig fig rule on here. This one had 4 sig figs. This one had 2. My answer should have how many sig figs?
2.
So how would you write this as 2 sig figs? You'll make it 120?
Yeah.
Correct? Plus, now we do the multiplication for these. So let's do 8 times 25.2. That gives you 201.6. That gives you 201.6. This one had only 1 sig fig. This one had 3 sig figs. Means your answer should only have 1 sig fig, right? So how would you write 201.6 as 1 sig fig? You will just write this as 200. Yeah? And then you would just blindly add them up. 120 plus 200 is how much?
300.
120. It's going to be 320. Now for plus and minus, you look at the numbers after the decimal. How many numbers were there after the decimal? 0. For this, 0. My answer should have 0. So that's my final answer. All good?
Yeah.
Okay, perfect. So that's a combination of plus and minus. Okay. Now, in the next question, they're saying round it to 3 sig figs. So you want to round it to 3 sig figs for the next questions that I'm going to write down. First one that they gave you was 0.009078. So as a first step, you want to write this as a scientific notation. So you want to put the decimal after the first non-zero number. So it will be 9.078 times 10 to the power. Okay, how many digits did you move? 1, 2, 3. But you moved 3 to the right. So it will be 10 to the power minus 3. Another way to know when you'll have a negative is whenever you see a decimal, which is a really small number, smaller than 1, way smaller than 1, you should know this power is going to be negative. Or because it moved to the right, you will say the power is negative. Now, when you look at this, right now you have 4 sig figs. Question said round it to 3 sig figs. So this is going to get 9.0, but instead of 7, you're going to make it 8. Because the next one is 8, so it gets rounded up, times 10 to the power minus 3. And now you only have 3 sig figs. Fairly simple. What if I had given you 3,555,800? So first you want to write this as scientific. So put the decimal after the first number, 3.555,800 times 10 to the power. Right now my decimal's here, 1, 2, 3, 4, 5, 6. Okay, but right now I have way too many sig figs. We have 1, 2, 3, 4, 5, 6, 7 sig figs. That's not going to fly. We only need 3 sig figs. So you would rewrite this as 3.55, but instead of 5, it will actually become 6 because the number after that is 5, so it'll get rounded up, times 10 to the power 6. And now you can see you have 3 sig figs here, you only have 3 sig figs here. So as you can see, your numbers for all of these, we're trying to make them to 3 sig figs. Okay, what if I give you 0.002358? So we first write this as scientific notation, 2.3548 times 10 to the power. How many places did I move? 1, 2, 3. So it's 10 to the power minus 3. I see we have way too many sig figs here. 1, 2, 3, 4, 5. We have 5 sig figs. We only want to have 3 sig figs. So you would say it's going to be 2.35 times 10 to the power minus 3. And there you go. You only have 3 sig figs now. Super simple. But if I give you 3.9004, you want only 3 sig figs? You want to write it as 3.90. That's it. Done. You have 3 sig figs. So that's how you're going to tackle your sig fig questions. Okay, this is just a recap of grade 11. I'm sure you guys did that in Chem 11 and Physics 11. And now we're going to move on to the real core topic of reaction kinetics. So the first thing we're going to talk about is reaction rates. Okay, the first thing we're going to talk about is reaction rates. How can we measure these reaction rates? There's several ways we can measure these reaction rates. First thing you need to know is this, okay? What's going to happen is you're going to have a bunch of reactants. Okay, I'm just going to make up some names here. Let's say you have some element A, it's mixing with some element B, and it's producing C. So these guys on your left-hand side are called your reactants. I'm going to call them R. R stands for reactants. So these are going to react and you will get your products. Moving forward, I'm going to just call the reactants R. I'm going to call products just P, okay? So you have your reactants to the left. We're going to call it R moving forward. And you have your products on the right. What will happen as this reaction goes on? As the reaction goes on, these reactants are going to start turning into products. So when these reactants start turning into products, what will happen to the reactants as time goes on? As time goes on, your reactants are going to decrease. And as time goes on, your products will start building up. So your products are going to increase. Does that make sense? So as reaction proceeds, as time goes on, your reactants are turning into products. That means your reactants will decrease and your products will increase. This is the first concept I want you to remember. As the reaction proceeds, as time goes on, reactants go down, they decrease, and the products go up, they increase, products increase. Is that clear so far?
Yeah.
Okay, good. Now, how can we measure reaction rates? What are the different ways you can measure the reaction rates? We're going to first talk about having solids on reactant side. What if your reactants are solids? If you ever see a solid on your reactant side, you can measure the reaction rate in this manner, okay? Reaction rate for a solid will be measured as change in mass over change in time. Because you know solids have a mass, right?
Mm-hmm.
So as time goes on, let's talk about this A. This is a solid right here. Let's talk about this A. It's a solid. As time goes on, what's going to happen to the mass of A? Because it gets used up, it's going to decrease. Exactly. So to be more specific, you would say if your reactant is a solid, then you can measure the reaction rate in terms of, okay, instead of change in mass, we're going to be more specific. It will be decrease in mass of your A, which is a solid, over change in time. Because you know it's a reactant, so it will decrease in mass. So if your reactant is a solid, how can you measure the reaction rate? You will say it's going to be change in mass over change in time. To be more specific, it will be decrease in mass of a solid over change in time. Does that make sense so far?
Yeah.
Okay, good. Now, what if your reactant is an aqueous solution? What if it's an aqueous solution? How can you measure the reaction rate for your aqueous reactants? Well, you should know your aqueous guys, they deal with concentration. So for those you can measure it as change in concentration. Change in concentration Now, moving forward, I'm going to, instead of this whole word concentration, I will just use these brackets. They stand for concentration, right? I will measure the change in concentration of B over change in time. Now, to be more specific, your B is a reactant. So as time goes on, it will get used up. So to be more specific, we're going to measure it as decrease in concentration of B over change in time. You know, your reactants always decrease as time goes on. Does that make sense?
Yeah.
So for solids, we can use mass. For aqueous guys, we can use concentration. Now, what about the gases? Well, for gases, you can use a bunch of different things. The first one is definitely concentration again. Gases have concentration as well. Aqueous guys have concentration, and gases have concentration too. So in this case, you know, your C is a gas, but C is a product. So you can say you can measure this as change in concentration of C over change in time. To be more specific, because your C is a product, it's going to go up, it's going to increase. So it will be increase in concentration of C over change in time. Okay, so once more, when it comes to solid, you will use change in mass over change in time. If your solid is a reactant, then it will be decrease in mass over change in time. If your solid has to be a product, then it must be increase in mass. Okay, in this case, we're talking about A, which is a reactant, so it was decrease in mass of A over change in time. When it comes to aqueous guys, then you use concentration. B is a reactant, so it will be decrease in concentration of B over change in time. For gases, you can use concentration. Concentration should be the first one that you can use for gases. There's a bunch of other things you can use for gases. Okay, you can use pressure. You can use volume. Okay, these are some of the other factors you can use, but the main thing for gas is still concentration. But in this case, your gas was a product, so it will be increase in concentration of C over change in time. So far, so good?
Yeah.
Okay, excellent. Now, apart from that, there's a bunch of other factors you can use, but as long as that's given to you in your equation, you can use a bunch of other factors as well, okay? I'm just going to list out those factors. You can use color. You can use color if your equation gives you color. And obviously, you can use pressure as well. We can use volume, okay? So these are some of the other characteristics that you can use to measure the reaction rate. So let's look at the specific examples now. Let's talk about the specific examples. My first question is, we have Mg solid reacting with 2HCl aqueous, and we have H2 gas. And my second product is MgCl2 aqueous. We want to see in how many different ways can I measure the reaction rate? Well, we're going to first start off with Mg. Mg is a solid, correct?
Mm-hmm.
So how can I measure the reaction rate in terms of Mg solid? As soon as we talk about solid, the first thing that you should remember is mass.
Mm-hmm.
When it comes to solids, first thing we think about is mass. So we can measure this as change in mass of Mg solid over change in time. Now, let's be more specific. It's a reactant. So when it comes to reactants, it will be decrease in mass of Mg solid. It will be decrease in mass of Mg solid over change in time. That would be your more specific question, more specific answer. Does that make sense?
Mm-hmm.
So we talked about Mg. Okay, let's move on. What about this HCl, aqueous? Well, when it comes to aqueous, guys, we're talking about concentration. So if you want to measure your reaction rate in terms of HCl, which is aqueous, then you would say we're going to measure it as change in concentration of HCl over change in time. Now, let's be more specific. HCl is also a reactant, so it will go down, it will decrease as time goes on. So it will be decrease in concentration of HCl over change in time. Okay, so we're good for that as well. Let's move on to this H2 gas, which we see on the product side. So how can I measure the reaction rate in terms of H2 gas? Well, you say it's a gas. Again, we can use concentration. So what's going to you can say I can measure it as change in concentration of H2 gas over change in time. Now let's be more specific. H2 gas is a product. It will increase as time goes on. So we will measure this as increase in concentration of H2 over change in time. Okay, next one we have is MgCl2. So how can we measure the reaction rate in terms of MgCl2? Well, MgCl2 is aqueous again. So guys, how can we measure reaction rate for aqueous, guys? We can measure it using concentration. So it will be change in concentration of MgCl2 over change in time. To be more specific, it's a product, so its concentration is going to increase. So it will be increase in concentration of MgCl2 over change in time. Do you understand this? So you see, we've been more specific over here, right? For each of those, for the reactants, they're going to decrease. The products are going to increase. For solid, we talk about mass. For aqueous, we talk about concentration. For gases, again, we talk about concentration. There's a bunch of other factors we can use for gases, such as pressure and volume, but we're going to talk about those afterwards. The main factor we use is still concentration for gases. So far, so good?
Yeah.
Excellent. Okay, so moving on to the next question, we have AgNO3 aqueous. We have AgNO3 aqueous. It's mixing up with NaCl aqueous. NaCl aqueous. And it produces NaNO3 aqueous. And the other product is AgCl solid. So that's my equation. Now the question says, okay, what are the different factors we can use for this? And more specifically, they're talking about ions. So this one's a bit tricky, okay? This one's a bit tricky. Let me explain you why. AgNO3, what's AgNO3 made up of? Well, it's made up of Ag plus ion and NO3 minus ion. Do you agree? Mm-hmm. What about NaCl? NaCl is made up of Na plus ion and Cl minus ion. What about NaNO3? Well, it's made up of Na plus ion and NO3 minus ion. This one's a solid, so you cannot break up a solid. You can only break up your aqueous guys, not your solid guys. Keep that in mind. Because you know your aqueous solutions are just dissolved in the liquid, right? They're just dissolved in water. So we cannot break our solids, but we can break up all our other aqueous guys. Now, one another thing to notice is I have Na plus on the reactant side, and I have Na plus, the same Na plus ion on the product side. Similarly, I have NO3 minus on reactant side, and I have NO3 minus ions on the reactant side. So what this means is we cannot use these ions. We cannot use our NO3 minus ion or Na plus ion because they show up on both sides. This is a symbol of because, okay? Because they show up on both sides. On both reactant and product sides. Another way of, you can say that these are called your spectator ions. Your spectator ions, they show up on both sides, so essentially they end up getting cancelled. So why cannot we use them? Well, they show up on both sides. If the same ion shows up on both sides, would you ever see a change? You won't see a change to NO3 minus or Na plus because it shows up on both sides, right? And the ratio is 1 to 1. Okay, so you cannot use them. So which ones can you use? You can use Ag plus. So you can say, you can measure your reaction rate as change in concentration of Ag plus over change in time. Now Ag plus is a reactant. So to be more specific, it will be decrease in concentration of Ag plus over change in time. Do you agree with that?
Yeah.
Okay, another one we can use is Cl minus, right? We can also use Cl minus. So we can say, we can measure the reaction rate as change in concentration of Cl minus over change in time. Now, Cl minus is also on the reactant side, so it will decrease as well. So it will be decrease in concentration of Cl minus over change in time. There's one other thing you can use. Look at this guy. AgCl solid. You see it's a solid?
Mm-hmm.
When it comes to solid, what do you think about?
Mass.
Mass. So we can also measure this as change in mass of AgCl solid over change in time.
Oh.
So we can also use change in mass of AgCl solid over change in time. To be more specific, because it's a product, it will be increase in mass of AgCl solid over change in time. Does that make sense?
Yeah.
Okay, so be careful. Whenever you have bunch of different ionic compounds combining to form another ionic compound, always ask yourself if you have any spectator ions, okay? So you won't use your spectator ions, you will only use the ones, because you know what's going to happen is Ag plus was the aqueous here, Cl minus was the aqueous, but then they went over there and they formed a solid. So what happened? The concentrations of Ag plus goes down, concentration of Cl minus goes down, and it becomes the mass of AgCl, right? So that's why you can use decrease in concentration for that, decrease in concentration for that, and increase in mass for that. Pretty simple, correct? Once you understand the concept, then it's fairly straightforward. Okay, let's move on to the next question now. In the next question, they have given you carbon solid, and it's reacting with O2 gas, and it's forming CO2 gas. Now the question says, what are the different things you can use to measure your reaction rate? Well, you know what? Let's start off with this solid. The C is a solid. So you should know this by now. What can we use for solid?
Mass.
Mass. So I can say we can measure this as change in mass of Cu solid over change in time. Now to be more specific, it will be decrease in mass because it's a reactant. So there will be decrease in mass of Cu solid over change in time. Correct?
Yeah.
Okay, we talked about that. Now let's move on to this O2 gas. Okay, when it comes to gases, what can we use?
Concentrate.
Concentration, yeah. So what will happen? You will say we can measure it as change in concentration of O2 over change in time. Now, to be more specific, because it's a reactant, it will be decreased in concentration of O2 over change in time. Correct?
Yeah.
Then let's move on to CO2. That's also a gas, so we can use concentration for that. So how can we measure the reaction rate in terms of CO2? You will say it will be change in concentration of CO2 over change in time. Okay? Change in concentration of CO2 over change in time. Now this one is a product, so it will be increase in concentration of CO2 over change in time. Correct? Pretty simple. Excellent. Let's move on to the next questions now. Now, these questions are tricky, folks, so I want you to pay attention. So they've given you 3H2, and it's a gas. It's reacting with N2 gas, and it's forming 2NH3 gas. Now the question says this. Okay, read this question. Question says, find each of the following reactions. For each of the following reactions, find a quantity or a property which could be monitored in order to measure the reaction rate. So, which quantity or property can you use to measure the reaction rate for these? Okay, this is interesting because you have all gases involved here, correct?
Mm-hmm.
You see there's all gases.
Yeah.
Now, I'm going to talk about the reaction rate in terms of my overall system. Okay? So ask yourself, how many moles of gases do you see here? How many moles of gases do you see here? There's a 3 in front, so you have 3 moles of gases. You have 3 moles of gas here, correct?
Yeah.
How many moles do you see on this one?
1.
Well, but no, this one is just 1 mole of gas. Okay? And what about over here?
2.
We have 2 moles of gas. Now, let's look at it in terms of the whole system. In total, your reactants had how many moles?
4.
3 plus 1 is? You have 4 moles of gases. And it went to how many moles?
2.
2. So you went from 4 moles of gas on the reactant side to 2 moles of gas on the product side, correct?
Yeah.
Okay, remember this. Whenever your number of moles go down, if your number of moles decrease, it means your pressure of the system will decrease as well. If your total number of moles of gas, they decrease, means your total pressure of the system will decrease as well. Keep that in mind. So how will you measure the reaction rate? You're going to say, I can measure the reaction rate as decrease in pressure of the whole system over change in time. I can measure it as decrease in pressure of the whole system over change in time. But there is one condition that needs to be true. If this needs to be held true, your system needs to be a closed system. It's very important that you write this. If you ever want to measure pressure, it needs to be a closed system. Let me give you an example. Let's say if you're boiling something, let's say if you're boiling water, and if you're boiling it in an open utensil, do you think will the pressure ever build up on that?
No.
No, because the water vapor is just going to keep escaping, right? And there's no lid on the utensil. So it's an open system. You can say it's an open system because your vapor, your gas is vanishing, right? So the pressure will never build up. However, if you do the same in a pressure cooker, remember when you cook stuff in a pressure cooker, all the liquid, it gets heated, turns into vapor, but it has nowhere to go. So pressure keeps on building up, and finally the pressure cooker goes.
Yeah.
Right? So if you ever want to measure the reaction rate in terms of pressure of the system, it will need to be a closed system. You will need to tell your teacher that it needs to be a closed system. As long as it is, then I can measure the reaction rate as decrease in pressure of the system over change in time. Why did my pressure decrease? Because my moles decreased.
Yeah.
Okay, my pressure decreased because my total number of moles decreased. Okay, good. Let's move on to the next one. So in the next question, I have CaCO3 solid. Now this is breaking up into CaO solid, and you have CO2 gas. So let's talk about the pressure of the whole system. How many moles of gases did you have on the left-hand side?
1.
For this solid? No. This is the common mistake. Is this a gas?
Oh, no, it's a solid.
So you have 0 mole of gas.
Okay.
Keep that in mind. A lot of students, they make this mistake. This is a solid, so you actually have 0 mole of gas here. What about this?
0 as well.
0, because it's not a gas, it's a solid, right? And this guy is 1 mole of gas. Excellent. So you can say in total, on my reactant side, I had 0 moles of gases. And I went from 0 to a total of 1. So your moles went up, your moles increased, which means your pressure of the system is going to increase. Correct? So how can you measure the reaction rate? Well, you can measure the reaction rate as increase in pressure of the system over change in time. But what's the condition that you're going to tell your teacher for this? What's the condition?
Closed system.
It has to be a closed system. Keep that in mind. If you don't write this down, you lose half of the marks. You will need to write it that it's a closed system. Now I have a question for you.
Yeah.
What if this was an open system? If this was an open system, what could you have used? What if this was an open system? Well, let's think about it logically. This was a solid. I want you to imagine you have this solid in a pressure cooker. But now it's not a pressure cooker. Now it's an open utensil because it's an open system.
Yeah.
So this, you're trying to heat this guy up, but this guy's forming a solid and a gas. What's going to happen to this gas if it's an open system?
It's gonna disappear, go out in the air.
The gas is going to disappear. It's going to vanish. Now, if the gas keeps on disappearing, what do you think is going to happen to the mass of the whole system?
Decrease.
Excellent. So we can also measure the reaction rate as decrease in mass of the system over change in time. But what's the condition for this? Condition for this is it will have to be an open system. Because if it's a closed system, will this gas ever disappear?
No.
If it's a closed system, the gas will never disappear. If the gas never disappears, the mass will never change.
Yeah.
Right? So here you go. You have two ways of describing the reaction rate. You can say if it's a closed system, then because my number of moles have gone up, my pressure of the system will go up as well. So then I can measure it as increase in pressure of the system over change in time. If it's an open system, then I know this was a solid. It produced a solid and a gas, but this gas will disappear, so my mass is going to start decreasing. In that case, you can measure it as decrease in mass of the system over change in time. Straightforward, correct?
Yeah.
Okay, excellent. Let's have a look at the next one. We have 2NO2 gas, and they say it's brown. And this turns into N2O4 gas. And this gas, they say, is colorless. Question is, what are the different properties that you can use to measure the reaction rate? Well, first, let's talk about the moles. How many moles of gas do I have on the left?
2.
2. On the right?
1.
My moles decreased, which means my pressure will decrease. My pressure of the whole system will decrease. Agreed?
Yeah.
So one way of measuring your reaction rate is by saying we measure decrease in pressure of the system over change in time. Okay, what's another way you can measure the reaction rate? You see, another interesting thing that happened is they gave you the color.
Mm-hmm.
So you can measure it as change in color over change in time, correct? In this one, you can also measure it as change in color over change in time. Now, what will happen? As this reaction goes on, this will go from brown to colorless.
Mm-hmm.
So as time goes on, what's going to happen? The intensity of brown is going to decrease, right?
Yeah.
So you can measure it as decrease in, you can say intensity of brown. Decrease in intensity of brown color over change in time. Does that make sense?
Yeah.
Now, sometimes your equation might say, okay, if this reaction keeps on going for a long time, what will the color be? What will the color of the solution be?
Colorless?
Colorless, exactly. Because eventually you'll have just products, right? So it will just be colorless. Makes sense? Good. What's another thing you can use? So we talked about the pressure of the system. We talked about color. Okay, so we covered both of them. Excellent. Now, I have a question for you. Can you use mass over here?
No, you can't.
You cannot, because both of them are gases.
Yeah.
If you had a solid which produced one solid and one gas, then you could have used that, but not in this case, because both are gases, okay? Excellent. Good. Now, this is a very typical question. Look at question number 3 on your screen. This is a very typical question that you can get on the test. What they've done is they've given you this equation where Be solid plus 2HCl became H2 gas plus BeCl2 aqueous. Question says this. Question says a piece of beryllium, which is Ve, is dropped into 1 liter HCl, and the following data was obtained. You see they've given you this time and mass right here.
Yeah.
And the question says, calculate the rate of reaction. Calculate the rate of reaction in grams per second for BE. So they want us to find the reaction rate in terms of grams of BE consumed per second. Grams of BE consumed per second. So I will say, okay, so they want me to write this reaction rate in terms of change in mass of BE over change in time, right? Because they said grams per second. Okay, so then I say, okay, let's find the change in mass of B. So let's first find change in mass of BE. Well, for that, I just look at my initial mass and I look at my final mass. I don't even look at my terms in the middle because I just want to look at my initial and final.
Mm-hmm.
If you look at it carefully, your final mass was 0.010. So you do your final mass, which is 0.010, minus your initial mass, which is 0.020, and you divide it by total time. What was your final time? 20 seconds. Initial time? 0. So what was your change in time? 20 minus 0. Agreed?
Yeah.
When you do that, you get 5 times 10 to the power minus 4 grams of BE per second. Now, you actually end up with a negative in front. Why? A negative means that it's going down, it's getting consumed.
Mm-hmm.
Okay, what does this negative signify? It signifies that it's getting consumed because it's a reactant, right?
Yeah.
So we've expressed the reaction rate in terms of grams of BE per second. That's what the question was asking. Now, in the second part, they're going to say, express it in terms of moles per second, moles of BE per second. So you say, okay, I have 5 times, I'm going to ignore the negative now because it just means consumed.
Yeah.
So I can say we have 5 times 10 to the power minus 4 grams of BE being consumed in 1 second. And they say express it in terms of moles per second. So what we need to do is we just need to convert these grams of BE into moles. I have grams at the top, I will put grams at the bottom. And then we will just need to find the molar mass of BE. We say 1 mole of BE gives me, what's the molar mass of BE? If you look at it on your periodic table, it's 9.0. And what happens? Grams of BE cancels. Then you will take 5 times 10 to the power minus 4. Make sure you put a bracket around it.
Mm-hmm.
5 times 10 to the power minus 4, and then you just divide it by 9. It will give you 5.56 times 10 to the power minus 5. And now it's expressed in moles of BE per second. So there you go. Now, you have to be careful. You know, your teachers are going to pick on you in terms of the sig figs. How many sig figs were there for 5? 1, right? So your answer should have only 1 sig fig because you're dividing. So you need to change your 5.56 into 6 times 10 to the power minus 5. Because some teachers might take marks off if you're not using proper sig figs. Now just remember, when I do these questions, I'm not going to pay too much attention to the sig figs. I want you to just remember your sig fig rules and make sure you look at those while you're writing your answers on the test. Okay? Now, they can ask you one other thing. In the next step, what they can say is, we found this reaction rate, right? We've expressed this reaction rate in terms of moles of BE per second. They might say, express it in terms of grams of H2 per second. They might say, express the reaction rate in terms of grams of H2 per second. So what we need to do is, you see, we got the reaction rate in terms of moles of BE per second.
Mm.
So I'm going to write it down. I'm going to say it's 6 times 10 to the power minus 5 moles of BE per second. Now using the molar ratio, I'm going to go from moles of BE to moles of H2 first. So look at this table. What's the number in front of BE?
0.
1, right? What's the number in front of H2? 1 as well. So what's the molar ratio?
Kind of BE 0 because it's a solid?
No. We're talking about moles.
Oh, okay.
So we're not talking about gas. We're talking about just what's the number, what's the ratio going to be, right?
Yeah,
This is 1. And, let me change it up. Actually, I'm going to, instead of H2, I'm going to say HCl. And you'll see why. Instead of, I'm going to say, okay, express it in terms of grams of HCl per second. So what's the number in front of BE? 1, right? And what's the number in front of HCl? You see 2. Agreed?
Yeah.
So when I go to this equation, I say, okay, now I gotta change it to moles of HCl. So I say, I have moles of BE at the top, I put moles of BE at the bottom. And then I know the number in front of BE is 1. So for 1 mole of BE, I get 2 moles of HCl. For 1 mole of BE, I get 2 moles of HCl. What's going to happen? Moles of BE cancels. Now I got moles of HCl, but they want me to express it in terms of grams of HCl. So now we got to change moles of HCl to grams. So I put 1 mole of HCl at the bottom. And now we just got to get the grams of molar mass of HCl. Okay, can you do me a favor? Can you get the molar mass of HCl? I think it's going to be 36.5, but all right. So we wanted to get the molar mass of HCl, which was 36.5 grams. So 1 mole of HCl gives me 36.5 grams of HCl. Moles of HCl cancels. So now what do we have to do? We have to take this number and we have to multiply it with 2 and then multiply it with 36.5 and we will express it in terms of grams of HCl per second. So let's do that. Bracket 6 times 10 to the power minus 5, bracket close, times 2 times 36.5. That gives me 4.38 times 10 to the power minus 3, and this is grams of HCl per second. Okay? This is grams of HCl per second, but there's one thing we need to be careful about. 6 times 10 to the power minus 5 has only 1 sig fig, so we need to change this to only 1 sig fig. So technically you would say this would become 4 times 10 to the power minus 3 grams of HCl per second. Okay? So just be mindful of the sig figs.
Yeah.
What I would do is I would first write my answer without any sig fig rules, and then afterwards I would change it to proper sig figs. Does that make sense?
Yeah.
Excellent. Good. Now the question says, what will happen to concentration of HCl as the reaction proceeds? So here's the equation. Question says, what will happen to the concentration of HCl as it proceeds? Can you explain me what will happen to the concentration of HCl? Excellent. Concentration of HCl will decrease because it's a reactant. It will get used up. What will happen to concentration of H2?
Increase.
Increase because it's a product. Concentration of BeCl2?
Increase.
Increase because it's a product. What will happen to mass of Be?
Decrease.
Excellent. Very good. Because it's a reactant. So that's how you're going to tackle these kind of questions. You will get this question on the test. Okay, it's usually on the test. Good. Excellent. Okay, guys, now let's have a look at these questions. Question says, when pentane, which is C5H12, is burned in air, it produces carbon dioxide and water. So C5H12, when you burn it in air, means when you mix it with oxygen. So you have C5H12, you mix it with oxygen, it gives you CO2 and H2O. CO2 and H2O. First thing, what we need to do is we need to balance this equation out, okay? That's all the question is going to say, okay? So you're going to have to balance it out yourself. C has 5 in front. I mean, there's 5 C's on the left, so we need to put a 5 here. Okay, then you ask yourself, okay, how many hydrogens do we have here? How many hydrogens do you see over here?
12.
12. Over there, I only see 2. So why don't we put a 6 there? Now ask yourself, how many oxygens are there on the right? 5 times 2 is 10, plus 6. 10 plus 6 is 16. Over here, I only see 2. So we just need to put 8 there. And we balance this equation. Perfect. Now, in the second part, they're saying if pentane is consumed at an average rate of 2.16 grams per second. In other words, they gave you the reaction rate of 2.16 grams per second of pentane, and pentane is C5H12. They're saying C5H12 is being consumed at this rate, and they want you to first change it to moles per second. They'll say, can you write it as moles per second? So we say, oh, all right. So we have 2.16 grams of C5H12 per second, means this is how much pentane is being used in 1 second. All we have to do is, we have grams at the top, we put grams at the bottom. And then we're going to say 1 mole of C5H12 gives you how much molar mass. If you look at the periodic table, it will be 72 grams. Then what happens? Well, the grams and grams cancel, so you have 2.16 divided by 72. If you divide it by 72, you will get 0.033, 0.0300, and now you've expressed it in terms of moles of C5H12 per second. So you've expressed this reaction rate in terms of moles per second. This is using proper statistics, by the way. Does that make sense?
Yeah.
Okay, good. In the next part, they're saying if pentane is consumed at a different rate, then they want you to find the rate in terms of oxygen's moles per second. So this was the A part. In the B part, they gave you reaction rate in terms of 0.030 moles of C5H12 per second. So, and they want you to express it in terms of moles of oxygen, moles of O2 per second. So you say, okay, I have 0.030 moles of C5H12 per second. This is per 1 second. And they want me to express it in terms of moles of O2. So, okay, I have moles of C5H12 at the top. I put those at the bottom because I want to cancel them out, right?
Mm-hmm.
Now, what's the number in front of C5H12? 1. And we want to go to moles of oxygen. And what's the number in front of oxygen? O2, 8. That means for 1 mole of pentane that you burn 8 moles of O2, oxygen, correct?
Yeah.
What happens? Moles of pentane cancels. So then you do 0.03 times 8. When you do that, you get 0.24. And that is 0.24 moles of O2 per second. So you've just expressed this reaction rate in terms of moles of O2 per second now. Does that make sense?
Yeah.
Okay. So in the C part, they're saying if pentane, so they've given you another reaction rate of pentane now. They said it's 0.030, same as the previous one actually. You're burning these many moles per second of pentane, which is C5H12. And they want you to express it in terms of moles of CO2. Moles of CO2 per second. Okay, very similar steps, guys. You're going to say we have 0.030. We have 0.030 moles of C5H2 per second. And we want to convert it to moles of CO2. So I have moles of C5H2. I put moles of C5H2 at the bottom. And I say okay, what's the number in front of C5H2? Let's look at our balanced equation. So the number in front of C5H2 is 1, and the number in front of CO2 is how much? 5. So for 1 mole of C5H2, I get 5 moles of CO2. Do you guys agree?
Yeah.
Moles of C5H2, moles of C5H2, it cancels out. So now we have 0.03 times 5. 0.03 times 5 will give you 0.15 moles of CO2 per second. We've expressed this reaction rate in terms of moles of CO2 per second now. So far, so good?
Yeah.
Okay, now let's have a look at the next part. In the next part, they have given you the reaction rate in terms of 0.030, again, moles of C5H2, C5H12, sorry. And they want you to express it in terms of grams of CO2 per second. So you say, okay, we have 0.030 moles of C5H2. This was per second, by the way. C5H12, I keep on saying C5H2 per second. And we want to change it to grams of CO2, but we cannot go from moles of C5H12 to grams of CO2 in one go. We're going to have to go from moles of C5H12 to moles of CO2 first. So I put my moles of C5H12 at the bottom. And the number in front is 1, and we want to go to moles of CO2, which is 5 moles of CO2. What happens over here is your moles of C5H12, moles of C5H12 cancels. And now we want to go from moles of CO2 to grams of CO2. So I put my moles of CO2 at the bottom. And I say for 1 mole of CO2, you get how many grams? What's the molar mass of CO2? 44. And then what happens? Your moles of CO2 cancels. If you do 0.030 multiplied with 5 multiplied with 44.0, you will get 6.6 grams of CO2 per second. So there you go. You will get these questions on the test. I guarantee you that. These reaction rate type of questions, you're going to get those on the test. Okay? So make sure you practice these questions, okay?
Yeah.
Excellent. Let's move on to the next topic now. Okay, guys, so what's happening over here is they've given you a bunch of reactants and products. So I'm going to write it in more generic form. If you have a reactant, which is an aqueous, and it's turning into a product, which is an aqueous, how will the graph of reactant concentration look like? So if you want to draw the graph of your reaction concentration of reactants over time, how will this look like? Let me explain it to you. In the beginning, you have lots of reactants. So it's going to be a high number. As the reaction goes on, you know these reactants start turning into products, right? So what happens is in the beginning, you have lots of reactants. There's lots of collisions happening. So the rate at which it's turning into products is really fast. Because the rate is really fast, it drops down really quickly. So you see it drop down real quick over here. As time goes on, you don't have too many reactants left. So there's very few reactants left. There's very few collisions happening. So your rate kind of slows down. You see this graph, the slope tapering off? The slope is getting smaller and smaller.
Yeah.
It means the reaction rate is slowing down. And, you know, it's going to slow down, and eventually it will just become a horizontal line. Okay? So this is how the concentration of a reactant is going to look like. In the beginning, you have tons of reactants, and they're going to drop. The concentration is going to drop. In the beginning, it's going to drop real fast. Afterwards, it's going to kind of slow down, and then taper off. Does that make sense?
Yeah.
Okay, now what's going to happen with the product? Okay, so let me give you the graph with the product now. How will this be? How will your concentration of product look like with respect to time? Now, you know, in the beginning, you have no products, right? So your products are 0.
Yeah.
Your reactants turn quickly into products, means your products rise up quickly. Afterwards, your reactants are slowing down, your rate is slowing down, so your buildup of products is slowing down, and eventually it tapers off as well. So if they ever ask you to draw the graph of the reactant concentration with time, or graph of any product with time, this is how it would look like. Do you understand it?
Yeah.
Okay, so as you can see over here, explain how you got that shape. You would say at first, you know, as you can read over here, at first the rate is really high because the concentration of HCl is high. So the slope is steeper. As the reaction proceeds, HCl is used up. So HCl concentration decreases, right? You see HCl concentration is decreasing?
Yeah.
But it's getting used up and the rate is slowing down. Because the rate is slowing down, the slope is slowing down as well. This is how you would describe that. Do you understand?
Yeah.
Okay, perfect. Okay, let's move on to the next topic now. Okay, guys, so in the next question, what they're telling you is you have 3 H2 molecules. You have 3 H2 molecules, and you have 3 O2 molecules, or 3 I2 molecules. And the question says, how many collisions are possible? How many collisions are possible? So let's think about it. What you have is you have 3 molecules of H2, right? So let me draw those out. First molecule of H2, second molecule of H2, third molecule of H2. And you have 3 molecules of I2. So you have first molecule of I2, second molecule of I2, third molecule of I2. Do you agree?
Yeah.
Now let's see how many collisions are possible. Well, this H2 molecule can collide with this, it can collide with this, or it can collide with this. So how many are possible for H2 and these ones in total? 3, right?
Yeah.
Same for the second one. The second guy can collide with this, collide with this, collide with this. So we got 3 more. 3 plus 3 is 6. Same for the third one. Can collide with this, can collide with this, can collide with that. So 3 more. So 3 plus 3 plus 3 is 9, right?
Yeah.
So there's 9 collisions possible. How many collisions are possible?
9.
9 collisions. Okay, what's a better way of getting this number rather than doing this one by one? The better way is 3 molecules of H2, 3 molecules of I2, 3 times 3 is 9. So if tomorrow they say I have 10 molecules of H2, 10 of I2, it would be 10 times 10, it would be 100 collisions. Understood?
Yeah.
Okay, perfect. Okay, so I want you to read this question. Question says, number 7, okay? Question says, in a room filled with H2 and O2, there are about 10 to the power 32 collisions per second. Okay, so you have lots of collisions happening. You have a bunch of H2s and O2s in a room, and they tell you that there's 10 raised to the power 32 collisions per second. Okay, what that means is that you have lots of collisions happening. You know, in a typical room, like the room that you and I are sitting in, there's a whole bunch of H2 and O2 molecules, right?
Yeah.
And there's tons of collisions happening. But why is there no reaction happening between H2 and O2? So question says, why the reaction between H2 and O2 at room temperature is so slow, so to be unnoticeable? Why aren't you noticing any reaction between them? Well, the reason for that is, you know, I'm going to introduce you to this now. If your reaction needs to be successful, okay, I'm going to draw, this is called your potential energy graph. Okay? This is called your potential energy graph. What's going to happen is, usually you have these reactants, and they need to cross this barrier to turn into products. These are your reactants, these are your products. This barrier right here, this barrier that they need to cross is called activation energy barrier. It's called EA, which is called your activation energy barrier. Let me explain it to you. This is called your activation energy. Activation energy barrier. That bump is called your activation energy barrier. If you want to have a successful reaction, if these reactants are to turn into the products, you need 2 conditions. Okay, remember this. I'm going to ask you this question later on again. You need 2 conditions. Your reactants need sufficient or enough energy. Your reactants need enough energy to cross, or you can say to overcome, the EA barrier. Your reactants need sufficient energy to overcome the EA barrier, which I've drawn right here. Means your reactants need to have enough energy to go past this barrier. Okay? The best way to think about it is, think of your reactants as skateboarders. You know, there's a hill. These skateboarders want to go past this hill. They need enough energy to go past this. If they don't, they're never going to make it through. Right? So if you want a successful reaction, if you want the reactants to successfully turn into products, they need to have enough energy to overcome this activation energy barrier. Okay? That's condition number one. On top of that, there's another condition which is called collision geometry. Means the orientation where these reactant molecules combine with each other. You know, when these reactant molecules combine with each other to become products, they need to react in a really nice manner. They need to be properly oriented in order to bond and become a product. Okay, so two conditions. If I'm going to ask you, moving forward, this is what I'm going to say. What are the conditions for successful reaction? What are the conditions required for successful reaction? So you're going to say condition number one is that your reactants need enough energy to cross, or you can say to overcome, the activation energy barrier, the EA barrier. The second condition is collision geometry. Means when these reactant molecules, they link up with each other, they need to have proper orientation.
Yeah.
Do you understand that?
Yeah.
Okay, good. Let's go back to this. Now, number 7 says that there were lots of collisions happening between H2 and O2 at room temperature. But why didn't you see any noticeable reaction? Well, you know what? Even though your collisions there were lots of collisions, but very few of those collisions are successful. Why? Because they probably didn't have enough energy to overcome the activation energy barrier. Because you need the energy, you need enough energy to go past the activation energy barrier. So even though there are lots of collisions happening, but they don't have enough energy, they still don't have enough energy to cross the activation energy barrier.
Yeah.
Okay, understood?
Yeah.
Okay, now we're going to talk about two ways of speeding up the reactions. We're going to talk about how can we speed up the reaction. So I'm going to draw this graph again. Okay, I'm going to draw this potential energy graph for you. They call them the EP graph. And this is our reactant. So these are our reactants right here, and these are our products. And as I explained it to you, this is called your activation energy barrier. Okay. How can you speed up the reaction? Okay, how can you speed up the reaction? How can you speed up the reaction? Well, I want you to remember this. The best way of speeding up any reaction is to increase the temperature. Remember this. What's the best way to increase any reaction is to increase the temperature. When you increase the temperature, what's going to happen is you see these reactants. When you increase the temperature, it will increase the energy of the reactants molecules. It will increase the energy of reactant molecules. So now what will happen is they will have enough energy to go past the barrier. Your reactant molecules will have enough energy to go past the EA barrier, to cross your EA barrier. Does that make sense?
Yeah.
So what's the best way of increasing speeding up any reaction? You increase the temperature. Another thing what you could do is you could add a catalyst. You could add a catalyst. And let me tell you what a catalyst is going to do. When you add a catalyst, what's going to happen is this catalyst is just going to lower this activation energy, It will have two bumps, or it usually has multiple bumps, but it lowers the activation energy. You see, it was so high. Your original activation barrier was quite high, but now if you look at the new activation energy barrier, it's super small now. Right? Your new activation barrier is super small. And when you add a catalyst, this is what it does. Adding a catalyst, it lowers your activation energy. Remember that. What does adding a catalyst do? Adding a catalyst, it lowers activation energy. Or in other words, what this does is, you can say it lowers EA, activation energy, or you can say it provides an alternative path. It provides an alternative path with lower energy, lower activation energy. It provides an alternative path with lower EA barrier. And because of that, the reaction speeds up. Because now a lot more of these reactant molecules are able to cross this barrier because it's lower, right? So a lot more of these reactant molecules can easily cross. So that's how it speeds up the reaction. Okay, so tell me the two factors that we just discussed. How can we speed up this reaction? We can increase the temperature, right?
Reduce the catalyst as well.
And we can add a catalyst. How does the increasing the temperature help? Well, when you increase the temperature, you're going to increase the energy of the reactant molecules. So now they have sufficient energy to go past the activation energy barrier. And what about a catalyst? A catalyst just provides an alternative path with lower activation energy. So it's a lot easier for your reactant molecules to go past it. So far, so good?
Yeah.
Okay, excellent, good. Now, oh, there's another thing you could have done. There's another thing you could have done. What might be done to a solid catalyst in order to make it more efficient? Okay, if you have a solid catalyst, what more can you do to make it more efficient? What you can do is, you can grind it into a powder. You can grind it into a powder. And how does this help? When you grind it down, you increase the surface area, right?
Yeah.
So think of a catalyst as a block of, think about it as a chalk, right? Think of catalyst as a chalk. Imagine you have a big block of chalk. The only thing that can react is the molecules which are on the outside surface, right?
Yeah.
But if you take this chalk and you crush it and you make it into a powder, now even the inner molecules are exposed. So even the inner molecules can react, they can collide. So how does increasing the surface area help? Increasing the surface area, okay, it exposes more molecules. So you have more molecules exposed. You have more molecules exposed, which allows for more collisions and faster reaction rate. Do you understand that?
Yeah.
So when you crush the powder, when you crush the chalk, even the inner molecules get exposed. So there's more collisions that can happen, and that speeds up the reaction as well. So remember this. First one we talked about was temperature. Second one we talked about was the catalyst. And the third one, well, if your catalyst is a solid, grind it and make it into a powder. It will make it more efficient because the surface area will be increased. Okay, good. Question number 9. This question is usually on the test. So I want you to remember this. Okay, I'm going to draw this out first. Now this, you have to realize this is not your potential energy graph that I'm drawing. On your y-axis, you have number of particles. You have number of particles. On your x-axis, you have kinetic energy. You have kinetic energy. What they've done is they've given you a graph. Okay, I'm going to make my original graph in white. So they've given you this original graph, okay? And this original graph has a activation energy, which is shown. This right here is your activation energy. So this is your activation energy. Does that make sense?
Yeah.
Question says, so what this tells you is that right now, these are your number of particles. This is your graph. This is the activation energy. So the only particles which are crossing this activation energy barrier are only these guys, right? These are the only guys which are successful so far. All of these guys are not successful. They never cleared the barrier. It's only these guys which ended up clearing this barrier of activation energy. Question says, on this diagram, how will this graph change if you increase the temperature? What will happen if you increase the temperature? What will happen if you increase the temperature? How will this graph change?
It'll speed up the reaction.
It will speed up the reaction. So more molecules will be passing the activation energy barrier, right?
Yeah.
So what's going to happen is this. I'm going to draw that in yellow. So this graph is going to get pushed to the right, and the peak is going to be a bit lower. It's going to be pushed to the right, and the peak is going to be a bit lower. And now, if you just extend this activation energy, so if I just extend this activation energy right here, let's say this was the activation energy, okay? And let me just relabel it. So this is my activation energy. I just extended it. You see, in the beginning, only the yellow guys were crossing over, right? But now look, there's a lot more guys which are crossing over, right? So a lot more guys are successful now. So you need to know how to graph this. So you need to know, as the temperature increases, this graph is going to get pushed to the right. The peak will be lower, but because it gets pushed to the right, there's more particles. Just 1 second. Yes. So because you increase the temperature, it got pushed to the right. What's going to happen is there's a lot more particles which have crossed now. See that? A lot more particles have crossed.
Yeah.
So it will get pushed to the right and it will be a bit lower. Remember that. You'll need to draw this out. Okay?
Yeah.
Excellent. Let's move on to the next part. Okay, so next up, what we're going to talk about is exothermic and endothermic reactions. You need to know these inside out. We're going to first start off with exothermic reactions. So, do you remember the definition of exothermic reaction? In exothermic reaction, heat is released into surroundings. In exothermic, heat is released into surroundings. I want you to remember that. You know, sometimes they might give you an example like a reaction happened and the surroundings got warmer. Was this exothermic or endothermic?
Exothermic.
Exactly, because heat was released, then surroundings will be warmer, right?
Yeah.
Surroundings gets warmer because it's released. If a reaction happens and surroundings get cooler, then it will be endothermic because it consumes heat from the surrounding. Endothermic consumes heat, okay? So how does the graph of exothermic look like? Okay, I want you to remember this. In exothermic, your products are lower than your reactants. Keep that in mind. In exothermic, your products are lower than your reactants. So let's say if your reactant was at maybe 10 joules and your product was at 2 joules, there is something called change in H, which is called your enthalpy. This change in H, which is your enthalpy, for exothermic, it's a negative number. How do we find our change in H? We always do energy of the product minus energy of the reactant. If you do it for this, you will see that it's a negative value. So keep that in mind. If your change in H is a negative value, it's an exothermic reaction.
Yeah.
And you will need to remember this graph. Okay, make sure you remember this graph by heart. Okay, so exothermic heat is released into the surroundings. The graph of exothermic looks like this. Your products are lower than your reactants in terms of your potential energy, and your change in H is a negative number. How do they usually write this equation? Well, they might usually say A, let's say it's aqueous, reacts with B. I'm just making these up. And they produce C. On the side, they will put change in H is negative 10 joules. As soon as you see change in H is a negative number, you should know it's exothermic. So that's one way they write the exothermic reaction. Now the same reaction, they could have written it like this. A aqueous plus B gas becomes C gas. And sometimes on the product side, they will put 10 joules. If you ever see your heat term on the product side, tell yourself it's going to be exothermic. So there's two ways they can write it. They can on the side say change in H is negative 10, which means your change in H is a negative value. Straight away, you should know it's exothermic. Or you might see the energy term on the product side, which means it's exothermic. Yeah. Now, they might try to trick you. They might try to trick you by doing this. They might say A aqueous plus B gas minus 10 joules is C gas. So a lot of people say, okay, my heat term is on the reactant side, so it must be endothermic. No, they've tried to trick you on here. In chemistry, you never want to put your heat term as a negative in the equation. So if you ever see a negative 10 value, you will move it to the other side. And on which side will it show up?
On the product.
On the product side. So straight away, you say it shows up on the product side, so it must be exothermic. Yeah. Does that make sense?
Yeah.
Okay, perfect. So remember, this is how you're going to write your exothermic reactions. Let's talk about endothermic now. What if we have endothermic reactions? Now we're going to talk about endothermic reactions. So, number one rule, heat is absorbed, surroundings are going to get cooler, change in H is going to be positive, and this graph is going to look totally different. So let's start off. Heat is absorbed from the surroundings. In endothermic, heat is absorbed. So my surroundings are going to get cooler because it's going to absorb heat from the surroundings. Your graph of endothermic will look like this. Now, your products are going to be higher than your reactants. Change in H is still the difference between energy of products and reactants, but this time around it will be a positive number. So if you ever see change in H written as a positive number, tell yourself it's going to be endothermic. Does that make sense?
Yeah.
Okay. Or sometimes you will see the endothermic energy written alongside reactants. So if you ever see energy term on the reactant side, tell yourself it's going to be endothermic. Yeah. Again, same for this question, they might trick you. They might say this minus 10 joules. So you say, okay, you know what, in chemistry, my energy term cannot be negative. So I'll have to move this 10 joules to the other side. It will show up on the reactant side. So it must be exothermic.
No, it's endothermic.
Endothermic, yes, endothermic. Yep. So it must be endothermic. Yeah. Excellent. Perfect. You're paying attention. Good. All right. So you understand exothermic and endothermic now, and the different ways they can write the equation in?
Yeah.
Excellent. Let's move on to the next topic now.
Wait, if it's...
All right. So looking at question number 10, it says when 2 moles of A react with 1 mole of B, a reaction occurs in which 3 moles of C are formed. So let's write this down. 2 moles of A, they react with 1 mole of B, and then they form 3 moles of C. And 34.5 kilojoules of heat is given off. Heat is given off. That's the key word, given off. So is it exothermic or endothermic?
This is exothermic.
Exothermic, right? So I can put my heat term over here. I can say it's 34.5 kilojoules. It's given off, right?
Mm-hmm.
Another way I could have written this equation was I could have said 2A plus B becomes 3C And on the side, I could have said my change in H is negative 34.5 kilojoules because for endo, my change in H is negative, right? That's another way I could have written that.
Yeah.
So the first part says you write the equation in the first form. Second part says write the equation in the second form. So we've done that, okay? And then the third part says write a thermochemical equation which shows what happens when 3 moles of C decompose to form 2 moles of A and 1 mole of B. So now what they're saying is write the equation to show when 3 moles of C, it decomposes, means it breaks up to form 2A and 1B. So this is what's going to happen, but your heat term was on C side, so you'll have to put it on the C side. Does that make sense?
So basically the equation just flips over.
Pretty much the whole equation reversed.
Yeah.
In the first equation, A and B combined to form C, and in this C part, your C broke up into A and B.
Mm-hmm. Yeah.
Okay, so that was that. So in the next part, they're saying, what would happen to the temperature of the surroundings if the reaction mentioned in part A, so this was your part A,
yeah,
was carried out? What will happen to the surroundings? Well, you know your reaction in part A, your reaction in part A is exothermic, right?
Yeah.
So what do you think will happen to the surroundings?
Get warmer.
Exactly. Surroundings get warmer.
Yeah.
Your surroundings get warmer. Okay? So, and the next part, in the last part, they say, sorry, in the next part, they say in reaction mentioned in question A, which has more enthalpy. So in part A, which has more enthalpy? Which side has more enthalpy?
What's that?
Yeah, I'll explain it to you. Which side has more enthalpy? Enthalpy is just another name for heat energy.
Oh.
Enthalpy means heat energy. Now, you know your part A was exothermic, right?
Yeah.
How does our graph for exothermic look like? It looks like this, remember?
Yeah, products lower than reactants.
So which side has more energy?
Reactants.
Which side is higher? Reactants. Which side has more energy? Your reactants have more enthalpy or more heat energy. Does that make sense?
Yeah.
Okay, sometimes they might say which side has lower energy, then you would say it's a product. So that's why it's important to remember the graphs for exothermic and endothermic. Okay? In the F part, they're saying, what's the meaning of enthalpy? So exactly what you just asked. What's the meaning of enthalpy? It's the heat content, the total energy contained in a system.
Mm-hmm.
Does that make sense?
Yeah.
Okay, what's the total, what's the meaning of enthalpy? Pretty much your heat energy or your heat content.
Yeah.
Okay, so that's it for today. Okay, make sure you recap all of this, and we'll cover the next of the topics, the rest of the topics actually in the next class.